from Queen Mary University of London, and is going to give a talk on self-similarity in the problem of recognizing the last record.
Okay. First of all, thank you, organizers, for this wonderful opportunity to talk to this community around Jean. And this way, congratulate Jean in person. I will be talking about problem which I was rarely talking about in this community, actually never. Okay, so thinking when we first met with Jean, my impression was that the starting point was minus infinity. However, I recollected that we first met in one wonderful place, by now legendary summer school, of which I keep very, very good memories. That was Santa Flora 2002, and certainly many of participants of this meeting were attending this school too. Well, since then, well, I would say our orbits had different polarity, but the intersection points were very, very exciting to me and very beneficial for my research, and also communication with John was always a pleasure. So this relation is probably best pictured by this photo from one of the conferences, showing that directions were really different, though. Okay, just the picture speaks for itself. Good. So today I will be talking about, well, the second title of my talk is CSP from the viewpoint of CSP. So the first CSP1 is the classical security problem about recognizing the last record of success. And the second CSP is combinatorial stochastic processes, the term introduced by Jim Pittman to name a big area of research. And so the talk is devoted to some classic sequential optimization problems, has 3 parts. Let's see how much I can make today. So the first part is variations on the full information best choice problem. The second part is about last record in randomly paced Bernoulli trials, including the case of Chinese restaurant process. And the third part is devoted to the sequential increasing subsequence and bin packing problems. The general idea behind these considerations, behind these models, is that some self-similarity feature of the triple space, time, and parameter allows one to reduce the dimension of the system and get a reasonably simple solution to the optimization problem. So, how to move controls now? Okay. Let's start with the last record problem. A series of trials occur at epochs of some random pacing process, Poisson process, or some more general process. And given a time limit, we're looking for a strategy, stopping time of online observer to maximize the probability of recognizing the last record or the last success at the very moment it appears. Now, in concrete applications, this record could be anything. It could be a record observation in the sense of the extreme value theory, some maximum or minimum, or even median. It could be a record defined in terms of some partial order. Under record, we can understand a splitting event of a special particle in a fragmentation process, or a newly occupied table in the Chinese restaurant process, or it could be something like a known species. So to discuss these things, we need some small piece of optimal stopping theory. And in a nutshell, it's just this, as described in textbooks by, say, Chow, Robin, Zygmunt, Sheriaev, Ferguson. In this problem, there are two quantities. First quantity is S0, is the probability that when you see a record and stop at record, this record is the last in the series of records. And the second is the value function, which tells you what is the best, what you can achieve if you continue optimally from a given position. So the optimal stopping theory says that in every situation, until you stop, you should compare S0 and V, whichever is bigger, and act accordingly. So mathematically, the value function is the smallest excessive measurand of the payoff function S0, and it satisfies some recursion, some dynamic Hamilton-Jacobi-Bellman equation, which in general very difficult to solve. However, there is one case where the solution is simple. So suppose we are in a situation where stopping on the next record is more beneficial than stopping on the current record. Then certainly we should continue. Other way around, if it turns that stopping on the next record is more beneficial than stopping now, and this situation will persist in the future, that is to say, when you pass to the next record, it will still be the case that stopping on the next, the stopping now is more beneficial than stopping next, then the first time when this occurs, that is to say, stopping now is better than stopping next, you should stop. So in general, the maximum of these two quantities, so S0 is the probability that the observed record is the last in the series, S1 is the probability that there is exactly one record in the future. So in general, we have this inequality that maximum of these two is not bigger than the value in the stopping problem, but if the set of states where S1 is bigger than S0 is closed in the sense of the theory of Markov chains, then the first time the process enters this collection of states is the optimal stopping time. This optimal stopping time is called myopic because all what you need to do in every situation is to compare the probability to win when you stop now with the probability to win if you stop by the next record opportunity. So to give some idea of what is first situation when this holds, the so-called monotone case of optimal stopping, and when it doesn't hold, let's consider a very, very simple token problem. Just recognize the last point of a classic Poisson process. So you observe Poisson process in real time. You have a time limit. Every Poisson point is a record, and you wish to recognize the last record just at the moment it appears. Now, if X is the expected number of yet unseen Poisson points, then S0 is just the probability that the number of Poisson points yet to come is 0. S1 is the probability that there is exactly one Poisson point. Now, you equate this and see that X should be equal to 1. And because as the time progresses, this X is getting smaller and smaller, we're in the monotone case. So it's optimal to stop as soon as the mean number of Poisson points to see is exactly equal to 1. So this is the optimal strategy. It's myopic, and the optimal winning probability with the strategy is 1 over E, provided the total number of Poisson points is at least 1. Okay, so now next example of non-monotone stopping problem. Consider what I would call Pascalized Chinese restaurant process. So this is a continuous time embedding of the Chinese restaurant process due to Feng, Hoppe, and Pittman. And the model actually is just this. Given a time limit, you observe a birth process with linear birth rate k plus nu, where in the Chinese restaurant process parameterization, nu is the quotient of theta and alpha, and you wish to stop at the last point of this process. So every point is considered as a success, as a record. Now the probability that your stop is successful when you see a record goes down, when the number of observed points is increasing. This is because the bigger population size, the more births are yet to occur. So the monotone case of optimal stopping fails. And for X, a natural size variable, the optimal choice between the action stop and continue will depend both on X and the number of points which you have already seen. The value function in this case appears to be the minimal solution to the Hamilton-Jacobi-Bellman equation, which in this case is differential equation of a quite complex structure, and it is intractable analytically and can be only done with computer. Still, if the size of the problem is very big, sufficiently big, then the winning probability will be still close to 1 over E. So 1 over E is a magic value in this kind of problem. And in my talk, I will discuss both types of problems: when you have monotone case and non-monotone case, when the decision variable is just a continuous variable driven by some self-similar process, or decision variable should also involve the number of some counting variable should be also included in the state of the process. So let's start with the classic Gilbert and Mastella full information problem, which is the following. There is an IID sequence of marks sampled from known continuous distribution. So let these marks be xi1 to xn, and you observe the sequence one by one until being willing to stop. When you stop, you win if the point you stop is the maximum of the whole series. So under the optimal strategy, as Gilbert and Mastella discovered, the probability to win is 0.58, so it's bigger than 1 over E. And there's actually the formula for this. But let's embed this in some self-similar process. So first of all, it will be more convenient, instead of maximum, consider the minimum. And because the distribution of marks doesn't matter, we can assume that the distribution is uniform on 0, 1. So a good model for this is the following. This is a model with infinitely many rails. Let's just consider a planar Poisson process. In this glass, 0.1 times 0 to infinity. And with generic atom of this process considered as a mark psi observed at time t. So in this picture, you see some collection of records. These are stars. And other black points are points of the Poisson process. So every time you see a record, the only thing which is important is the number of Poisson points which satisfy the decreasing constraint. That is the area of the box psi times 1 minus t, which is the decision variable. So in essence, the Poissonization in this problem brings self-similarity feature. The box area process along a sequence of Poisson records is a self-similar process that it has some erosion, it has some drift, and suddenly it breaks according to uniform stick breaking. So this kind of process is in much more general form, is described in Jean's book on fragmentation. Okay, so we have now one decision variable and can think how to stop the process. It's quite natural to consider here hyperbolic boundary of the kind B of t is some parameter over 1 minus t. So the first time the record process, these are stars on this picture, enter this area, you should stop. There are two ways the record process can enter the stopping domain. Well, first of all, the record process can enter by drift. So when, well, in terms of fragmenting particle, the particle can erode to the mass, to some critical mass, which is this hyperbolic curve, or there could be a jump. So the particle breaks and the curve is broken. So after breaking this critical line, you should stop. And the two quantities of interest are the probability that you win. This is the probability that you will see no more records. It's just e to the power 1 minus X, where X is the area of the box of the small rectangle, which still remains. And the second quantity is a probability we will see exactly one record. It is this exponential integral. And from this, it's very easy to calculate the probability to win with arbitrary hyperbolic boundary is given by this type of integral. Two terms correspond to the situation when the stopping boundary is hit by a drift, or the stopping boundary is passed by a jump. So optimizing here, it's possible to find that the optimal parameter of the stopping boundary is something like 0.8. It's found from this equation, and because this integral is increasing when the upper bound is increasing, the stopping problem is monotone. So this myopic policy compare the probability to win when you stop now and you stop at the next record opportunity. This myopic policy is optimal. Well, calculating the winning probability, we get this formula, which was discovered long ago by Steve Samuels using some four-dimensional integration. Okay, for the problem of finite size, if we consider Poisson process with some time limit, not infinitely many arrivals, but just some limited number of arrivals, this formula should be just modified by replacing the infinite integration bound by the size parameter of the problem by the x. So that's the mean number of Poisson points. Now this story can be generalized in various ways. Well, let's look what can we do with a partial order. So now suppose that the marks are sampled from some partially ordered probability space, which has some kind of self-similarity. And well, when we have a partial order, naturally we need some concept of a record. What is a record in a partial order? There are many definitions, possible definitions of a record. A record is something which is better than all what you have seen so far. If it is in many dimensions, a record could be something which is better in one of the components and so on, but I will give a kind of more straightforward definition. Let's call a record a point which beats all previous records with respect to the partial order. So it's recursive definition. The first point is a record, then you wait until record is broken. Okay, that's a new record. Then you wait until this record is broken and so on. And so you construct a so-called greedy chain in the random sample. Okay, so the last record problem in this context would be to find a stopping time which stops on the last record within a given time limit. Well, I said to solve the problem explicitly, we need some kind of self-similarity, and suppose that your sampling space, our sampling space is self-similar in the sense that the uppercuts of every point are the same ordered probability spaces under some measure normalization. So conditionally, so if we normalize the measure of the space to be one, they're all isomorphic. So for instance, we can take a square or cube in n dimensions, in d dimensions, and put the Lebesgue measure, then this will be a self-similar partially ordered space because all boxes, all uppercuts, which are some rectangles or parallelepipeds, they're all the same up to scaling, measure scaling. Okay, so suppose we have this kind of situation, then we can formulate the problem with infinitely many arrivals in the style of Bertrand-Caballero entrance law. Well, they consider entrance law from 0 plus. We need some entrance law from infinity by passing to logarithm, but in essence, this is the same. So given this setting, we have some piecewise deterministic Markov process, which evolves as follows. It drifts to 0 at unit speed. Unit speed can be always achieved by time change, and suddenly stick breaks at unit rate. When stick breaks occurs, then the state variable is multiplied by some other random variable, which is the same for all breaking events. Now it can be shown that the last record problem in the setting is always monotone, and the optimal myopic stopping strategy stops at the first record when the size variable, which is the remaining time times the measure of the upper cut at a record, doesn't exceed certain bound. Now, this bound can be found from solution of this simple equation, and the value function can be written down explicitly. In some cases, in general, we have some Hamilton-Jacobi-Bellman equation which is unsolvable, but it can be solved explicitly in some cases. And the eminent case is the case of beta stick breaking with this density, in which case the value function is given explicitly in terms of the incomplete gamma function. The value is always bigger than 1 over e. So 1 over e appears this time as a bound. And it evolves as follows when we change the parameter of beta distribution. So if theta goes to 0, then the value on infinite sample is going to 1. The classic case is theta equals 1, settled by Gilbert and Masteller and Samuels. And when you move theta to infinity, then the value will converge to 1 over e. So in some sense, this model bridges the so-called no information security problem, where you know nothing about observations except of ranking them, and the full information when you know that the points are sampled from a given probability distribution. Recently, it turned that the case theta equals 1/2 appears as a limit in some optimal stopping problem with a drift. So that's when you sample random values from a uniform distribution. This uniform distribution is different for every observation. So there is some drift there. Okay. That was the first part of my talk, where I considered problems where only state variable counts. Now I pass to another kind of a setting, where also we need to take into consideration the number of points which have been observed to date. So the setting is the following. The parameters are 2 infinite sequences. Both are probabilities. The first is a success profile. So when you see a point number k, it is a success or a record with probability pk. And we assume that the success events are independent of anything else, also of the observation time. And the trials occur in continuous time according to some random process, and the total number of trials has some prior distribution. This is pi. The conditions which we need to impose on profile of successes p and pi are quite mild. So let's, to have problem non-trivial, assume that potentially there are infinitely many records. That's to say the series of p's is diverging. So we observe in time a series of trials. Each trial is a record with certain probability, independently of anything else. And the trials occur in continuous time according to some pacing process, which I will assume to be a mixed binomial. So more specifically, we can assume that the prior is a power series distribution, as advertised yesterday in Jim's talk. So every probability distribution can be extended to a family of power series distributions. So suppose we are given some collection of weights W and consider probability distributions of this kind. So the Q, which appears here, is a parameter, which is kind of a size parameter of the problem. So the bigger Q, the bigger the random variable. And we assume that pi n the total number of trials, and the process is mixed binomial, which in essence means the following. So suppose we fix the time from 0 to 1 and spread uniform points to be arrival times. So we sample n from the prior pi and spread n uniform points of the unit intervals. This is the arrival process. In particular, it could be any mixed Poisson, any Cox process. So it could be Poisson process, or if you change random lambda for Poisson distribution, we get the Cox process. It's all covered by this mixed binomial model. So we have two parameters, the success profile and the prior distribution, and we consider the problem of stopping and the last success in the process of observation of these trials. Okay, so what is this model actually? The posterior distribution of the number of unseen trials follows this familiar Rao-Rubin damage model known in statistical censoring and reliability models, and it is just that. If at time t, the number of seen trials was k, then the number of trials yet to be seen is given by this posterior distribution. So this point process n has this conditional distribution where f is some normalizing function here, and the substantial part is that. So 1 minus t is the time to go. So we are in time t, and the time which remains is 1 minus t, and we should multiply this by q, and q is a parameter of the distribution. This is where the self-similarity comes appears. So in place of considering time and this q parameter separately, we consider them as a sole variable, and this is actually the only important thing to be counted by the stopping strategies. Okay, so with this prior, we can consider various success profiles. What are classic success profiles? Well, perhaps of course, the most classic is just a constant. So that's a series of homogeneous Bernoulli trials. It's not most exciting. More interesting is to consider profiles like Rennie's profile for records. A record is a record, case trial is a record with probability 1 over k. One variation of this is Nevzorov's F alpha model, where there's a series of constants alpha, and pk is defined as a quotient. So in particular, when all alphas are equal, we are back to the standard extreme theory record model. Now, there's a very interesting profile which has no name. So we yesterday just discussed how to name it. So probably it should be called Karamata-Stirling after after this term appeared in a paper of Nick Bingham. So this profile pk is theta over theta plus k minus 1, very important in many combinatorial constructions underlying the classic Poisson-Dirichlet distribution, gem distribution, records, random mappings, and so on. Another possibility is consider malus measures on permutations, and records for malus measures, and then this leads to this other profile of success probabilities, which is closely related to Q exchangeable probabilities, to Q analysis, actually to Q analogs of many classical things. Okay, so with profile of success is fixed and with the prior fixed, we consider the stopping problem, and let's see what are the quantities of interest. So the probability generating function of the number of records which follow some state tk, that means that at time t we have seen k trials, then the number of records to be seen has this power series probability generating function, and the quantities of interest are obtained by expanding at 0. So the probability that you will see no records in the future S naught is of the form some function of x, some function which doesn't matter much, times some power series pk, and the probability that you will see exactly one record in the future is given by f times another power series. Now what comes here, if suppose for a while that we have some discrete time, and we have seen k trials and there are still j trials to come, then the probability that there are no successes in the series is given by this product, which is obvious, and the probability that we will see exactly one is given by this. So you take this as naught and multiply by this sum, which some people call the sum of odds. Okay, and so you need to compare these two quantities, and the problem will be monotone. If one is bigger than the other, then this will occur also in the future, and non-monotone if this doesn't happen. Okay, so now we go in the realm of power series, and monotonicity means the following: that you look at the equation as naught equals x1, the chance that you see no future records and the chance that you will see exactly one future record. Now this equation can be cast as a quotient equation. This one power series divided by another power series equals to 1. And it turns, if this quotient, if this equation has exactly one positive root, and it can have at most one positive root, then the problem is monotone, and typically there is exactly one positive root. Now, if we can solve this equation and find its solution for every k, then the optimal stopping time is the following. We should calculate for each q the so-called cutoffs, ak, which are now between 0 and 1. And if these things are decreasing, so if the roots of this are increasing, then the cutoffs are decreasing, then the problem is monotone, and the myopic policy stop at the first time when the time is bigger than the appropriate cutoff. So you see a record, you look at the index of this record, that is what is this record in the series of trials. So you look at the trial number, not on the record number, but the trial number, and depending on this number, you compare the time of observation with the cutoff, and if it is bigger, you should stop. Okay. Now, this actually has been done in the classic case, in the classic profile case, pk equals 1k. So this last record problem, under the name of secret or best choice problem, was studied by many people for priors like Poisson, by Kovan-Zapchik, Tiselsky-Zapchik, and other people. In the case when the prior was geometric, by Bruce Samuels, Bruce Rogers. In the case when the prior is negative binomial, in unpublished paper by Sid Brown, by Kuroshima Ano. And recently, in somewhat disguised form, the problem appeared for the log series distribution in papers by Bruce and Yor and Bruce and Rogers. And recently, we reconsidered this with my student. Also, discrete uniform case was studied long ago by Stewart and more recently by Tamaki Wang. In the large sample limit, it's always the case that the probability of win will go to 1 over e. But this limit is not most exciting. Let's look what happens in pre-limit case. Well, first of all, suppose the problem is monotone. That means that the stopping time is given by a series of cutoffs. So for problem of finite size, only finitely many cutoffs may be important, and maybe infinitely many, it depends. And each cutoff defines the earliest time when the stopping time, optimal stopping time, starts to accept a record at some index. So suppose we have some cutoffs optimal or not, how to compute the winning probability? Well, there is a formula for that. And the idea to compute winning probability is related to, not to the stopping time, but the some hitting time of, which I would call precursor of the stopping time. Tau, this is the earliest time when the process enters the area when you are willing to stop, in case a record will appear. So in terms of this stopping time sigma, the distribution of the stopping time can be calculated using some combinatorics. And the distribution is given by this integral formula. So if the number of arrivals is n, conditional on the number of arrivals n, that's a mistake. It should be n1, conditional on the total number of arrivals n. the distribution of the precursor time is given by that. And given this distribution, it's possible to calculate the winning probability. So in the monotone case, we have full control on the situation. We need to calculate the roots of certain equations in terms of power series. And then using this formula, calculate the winning probability. Let's see how it goes in the Karamata-Stirling case. So recall that Karamata-Stirling profile is given by this with parameter theta, and suppose that the prior is negative binomial. That's actually most exciting situation when it's negative binomial for many reasons. Well, we consider the parameter of negative binomial distribution to be nu, and this nu could be zero. Like nu equals zero corresponds to the log series distribution with weights 1 over n. So now when we're in this situation, what is the pacing process? The pacing process turns to be the Poyer-Lundberg process, which is a pure birth process with birth rate given by this formula. So nu comes as parameter of negative binomial distribution, and q is second parameter of negative binomial distribution, which determines the size of the problem, and the rate is just given by this. Well, and you see that it's really very convenient to set this process on the interval from 0 to 1, because you can manipulate this q. So you can send this q to 1, and then the limit will be some kind of self-similar process. Okay, so in this setting, the posterior is very convenient. So having observed k points at time t, the posterior is again negative binomial, but with just shifted parameter. The first parameter is nu plus k, and the second parameter is the size parameter, 1 minus t times q. Okay, so what are the power series? Well, first, let's look at one very special case. So suppose theta is equal to nu. If theta, so theta is parameter of the success profile, this is Karamata-Stirling Humans parameter, and nu is parameter of negative binomial distribution. When theta is equal to nu, then the point process of records turns to be Poisson. Why? Well, we just calculate the probability that the next point is a record, and it turns that this probability, this compensator, is deterministic. Therefore, by Watanabe's theorem, the point process of records is Poisson. And how to stop the Poisson process at the last point, we know how to do. We should wait until there will remain on the average exactly 1 point to get observed. So in this case, 1 record to be observed. So all cutoffs, all roots in this case are equal, and they're equal to this number, which generalizes the famous 1 over e. So parameter theta comes eminently in this formula. So the real-time cutoffs are all equal, are given by that, or equal. Yes, well, it depends on q. So if q is very small, it should stop immediately. So the cutoffs are at 0, but in general, they're just all coinciding. And when the problem is of sufficiently big size, the probability to win is exactly 1 over e. So what will happen if theta is distinct from nu? Well, now we are in kind of a trouble because we need to do some calculation. So let's look at the probability generating function of the number of successes after certain time. Or using the metaphor of Chinese restaurant process, we fix a time. We know that the number of arrivals have been k, and we're interested what is the number of new tables yet to come. Now, the probability generating function for this occurs to be some standard multiple of the Gaussian hypergeometric with parameters. So lambda here is the parameter of the PGF, k is the number of points you have seen, nu is the parameter of the arrival process, and theta is parameter of the Eulen's distribution. So looking at this, we need S0 and S1, the probability that no new tables or new successes will appear, the probability that exactly 1 new table will appear in the future. So the first is this hypergeometric function. This is P. And the second is more complex. It's a parameter derivative of the hypergeometric function in the first variable. So to find the roots, we need to solve this equation. Take the logarithmic derivative of the Gaussian hypergeometric function in the parameter, equate it to constant, and see how the solution depends on k. Now, it turns that the roots always converging to 1 minus e to the power minus 1 over theta. Yeah, recall that these are roots, not cutoffs. So when you pass to cutoffs, you should revert the time, and the cutoffs will converge to scaling version of e to the minus 1 over theta. And it turns that the difference between the roots and this limit has the same sign as the difference between nu and theta. So the stopping problem is automatically not monotone if nu, the arrival parameter, is less than theta, and we need to show that it is monotone otherwise. And this turns to be a very hard analytical problem, which can be solved explicitly in some polynomial case. So suppose that the difference between nu and theta is some integer. In this case, the Gaussian hypergeometric function turns out to be the polynomial. This is just Jacobi polynomial. In the standard parametrization of Jacobi polynomials, the signature m is the difference between nu and theta, and the signature of Jacobi polynomial is this. Okay, and then there's some change variable which is not that substantial. And in this case, we have very nice tools like Rodriguez formula, like theorem by Fröhlich, which gives explicitly formula for the parameter derivative, which can be used. And it turns that using this stuff, it can be shown that the problem is monotone, that is, the roots are increasing to this number, and so this problem is solvable in this case. I think it was Michael Keane who said once that each talk should have a theorem and a joke. So you see here a formula for high derivative of some rational function. So this is d in x of degree n plus 1, and you need to differentiate this thing. Now, this formula is not a joke, but a very nice exercise in calculus. And actually, you can teach students probably to differentiate quotients by first differentiating multiply the numerator, then multiplying out the results. Well, just take computer and convince yourself that this formula is true. Okay, so if the problem is monotone, we know what to do with that. If the problem is not monotone, what alternative could be offered to the choice between stop now and stop next? A good alternative is the trapping. So suppose we are in some state, tk means that time t has passed, we have observed k trials, and we wish now to guess where is the next record. A good strategy would be the following. We specify some time domain in the future and wait until a record will hit this domain, and then we stop. It's very natural to specify just some interval, some final interval from, say, t is the current time, to 1 with some parameter z. So z is a proportion of the remaining time which you are willing to skip. So what's the probability that you will trap the last record using this? This probability turns out to be a mixture of Bernstein polynomials. So this is posterior distribution of the number of trials to come. And this is the Bernstein polynomial interpolating this combinatorial function S1, and we're interested in features of this thing and in general in what maybe this trap, this interval trap is just not optimal. Okay, this turns out to be the problem related to the issue of unimodularity of some power series and convexity. So the probability of exactly one record is given by this formula. And this thing is unimodal in the parameter j. So k is something which you have seen, and j are yet to come. So this combinatorial thing is unimodal in j. Now you take a Bernstein polynomial of this thing. It is this. And by the shape-preserving properties of Bernstein polynomials, going back to Schoenberg and Poya, this thing is again unimodal. But when you take a mixture of Bernstein polynomials, this may not be unimodal. And actually, it's not hard to construct examples when the mixture of this, well, we can find some success probabilities and some priors when this mixture is not unimodal. When it is unimodal, well, the most simple condition for unimodality is to require that this S1 is concave, because the mixture of concave functions is certainly concave. The concavity condition is in essence this. So it takes two neighboring success probabilities, pk and pk plus 1, nothing else. And there are two inequalities. Looking at the range in the unit square, it is this length. It's rather small region. So if the pk plus 1 hit this region, then this combinatorial function S1 will be concave function. In particular, if you check these inequalities for the Karamata-Stirling profile, it turns that they are satisfied precisely for theta between 1/2 and 1. Otherwise, unimodality doesn't hold. Now, if this unimodality holds, then for any possible prior, the optimal trap will be a final interval. And there is no idea what can happen if this condition doesn't hold. Okay, so I'm finishing the second part. To summarize, we discussed monotone case and monotone case, and can ask what will happen if the problem is big. So I said, if the problem is big, the big sample typical value, no matter what is the success profile and no matter what's the prior, will be close to 1/e. Well, that's probably not very high probability for getting the last success. Certainly we need something higher, then we should not be so selective. So if the problem is modified a little bit so that we consider a series of trials when different types of trials are considered as successes, then of course this probability can be increased. For instance, if we are looking for a rare butterfly or for a nice theorem as possibilities, there are two types of successes. And if we are happy with any of this, then our chance to get one of the last in one of the series will increase to 50%. And more generally, if there are different types of records, this will increase to this number, which is close to, well, this is kind of, when r goes to 1, it is precisely 1/e. When r goes to infinity, this goes to 1. So depending on the preferences of the observer, the appropriate model can be used. Okay, I have apparently very little time, so I will just sketch a few things concerning another combinatorial problem where self-similarity turns important. So everybody knows the longest increasing subsequence problem due to Ullmann and Hammersley. So given a permutation or given a planar Poisson process, pick the longest possible chain there. The chain is a sequence of points which is increasing in both coordinates. And this problem has a nice online version, which was first considered by Bayer-Brock for permutations, by Samuels and Steele in Poisson case, and by many people thereafter. It is the following. You have a Poisson process in a rectangle, planar Poisson process. You scan this process left to right, and when you observe a certain point, you can select it or reject it. The objective is to select as many points as possible, but these points should be increasing. So increasing in both coordinates, in time coordinate and in the value coordinate, in the mark. There are versions of this, of course. You can consider D dimensions, or you can consider certain bin packing problems, which are all converging to the same self-similar model. I would cast this model as Halmos did in 44, using the metaphor of random atoms. So there is a pound of gold dust to be distributed among petitioners. The petitioners are arriving at random and requesting a random portion of the remaining treasure. Given a time limit, the objective of distributor is to serve as many applicants as possible by rejecting those which demand too much of the treasure, but keeping an eye on the clock, because it might happen that somebody comes, demands too much, but the time is running short. So it's better to satisfy the request than to reject it. Now, the uniform portion corresponds to the online increasing subsequence problem or a special bin packing problem. The non-uniform portion appears in other models. And in essence, this is the fragmentation problem of the kind. You have fragmentation process where there is a particle losing suddenly a portion of the mass. At certain times, the particle says, I wish to lose a part of the mass. And you say, you should not. And then it lives further. Then there's another request. And at a certain time, you say, OK, you can lose a part of the mass. The mass is lost. The particle keeps living and so on until some time limit. And you aim to have as many splits as possible within a given time limit. So presuming that the splitting is uniform, the corresponding Hamilton-Jacobi-Bellman equation is this. And this has a more or less explicit asymptotic solution given by this expansion. And you see here root 2t. So t is the size of the problem. That's time horizon or the value of this self-similar variable. And if we had here 2 root t, this would correspond to the length of the longest increasing subsequence. But because we are in the online situation, we have some profit to gambler factor, which is root 2. But unlike the classical Hammersley-Ulam problem, we can actually develop the full asymptotic expansion up to some constant, which is still unknown. So it goes like that. The first term is power. The second is logarithmic. In Ulam-Hammersley, the next term is again a power, t to the -1/6. And nobody knows what happens then in Ulam-Hammersley. And here we have the full expansion. We have the full expansion of the variance. And actually, using some kind of nonlinear renewal theorem, it's possible to show the central limit theorem for the longest chain, or the number of petitioners satisfied, or the number of splits of a particle in fragmentation process, and even get some functional central limit for the fluctuation of two quantities, the number of accepted petitioners and the running maximum process. So this two variable process is converging to some kind of two-dimensional Ornstein-Uhlenbeck process. Okay, so I think my time is over, so I will move quickly to the last slide. Thank you, and happy birthday, John.
Thank you for a very nice talk. So do we have questions, comments? Yep.
Thank you, Sasha.
Okay.
So if I understood properly, if instead of looking at stopping at the record, if you allow yourself to stop at one of the two best or one of the K best, it doesn't change that much. What if now you are paying a fine depending on the distance? I mean, how many steps separate the moment of your stop to the actual record? How many further record you can still see? Can you adapt your methods?
Okay, we should be very, very careful. If you have a sequence of rankable trials, so each can be, say you observe permutation, but you don't see the value of permutation, then only rank the value with respect to the past. Then if you are interested in the top or second top, then the optimal strategy has two cutoffs, and the success probability, this is so-called Gussein-Zadeh problem, will be 0.57. What I was talking about is different. You have two traits. You wish to get either the last green or the last red. In this case, the optimal strategy is in essence single cutoff, and your chance to win is 1/2, and is given by this generalized formula for more traits. What you asked about the last was the so-called Robin's problem. You look at the rank of the stopped point. So if, say, you get the 5th best, your payoff is 5, and you wish to minimize this payoff. In this case, the best strategy is given by infinitely many well, it is solved if you consider it in the no information situation with the value equal to 3.86. This is Chow, Robbins, Marigutti, and Samuels, 61 or 64. And if you observe the values of the trial, so if you sample, say, from the uniform distribution, this is so-called Robbins problem with a value close to 1, which is still unsolved. So it's some 30 years, it's still unsolved. Okay. So that's the general picture of this.
Oh, thank you. Very, very comprehensive. Thank you.
Do we have other questions? So maybe I have a very quick question. So about your online longest increasing subsequence problem.
Yeah.
I was quite surprised, in fact, that you can get an almost optimal. You almost get to the square root 2t bound. But do you have an intuition, a heuristic explanation for the fact that it's the fluctuations are Gaussian in the limit?
Well, so roughly speaking, so if you're only interested in the principal term, you just specify a window of the size root 2 divided by t, and wait until first point will hit the window. Then you take this as a base and move window up, and so on and so on. So in essence, you have here a compound Poisson process, and it's clear that it's in the domain of the central limit theorem. Yeah. If you are interested in the second term, then you need to build. Then this running maximum process will be just in the limit the Brownian bridge. Well, with some coefficient, but this will be a Brownian bridge. And the number of selections is some accompanying process, which is not Markovian, but it's still Gaussian. So we're here in the realm of the classical central, in the domain of attraction of the classical central limit theorem, roughly because the selections in different times are independent or close to be independent. That's the difference. That's the difference with this story about the longest, because they have then some repulsion between the points, and therefore there is no independence.
Mm-hmm. Okay, thank you very much. So I suggest we thank Sasha again. de toute façon, tu peux le déspotlighter.
Je vais spotlighter, mais il faut que je me retire ces trucs host, mais je sais pas si je peux le faire pendant que
Ok, super. C'est bon là?
ça marche pas.